Hi there, and welcome back to the channel. Throughout this series of videos, you will be introduced to topics in optimal control and estimation in a way that you can draw almost complete idea about optimal control and optimal observers. Most of the introduced materials during this journey is borrowed from the book, Applied Optimal Control, Optimization, Estimation, and Control, which written by Arthur Bryson. This is the second part of this series. But, before jumping into the subject of this video, let me briefly go through the topic introduced by part 1 of this series. In part 1, we have covered parameterized optimization when there are no constraints. A link for this topic is given in the description. The problem is as follows: we have a scalar function capital L, called the index of performance that has m parameters or variables u1 through um. We assume that there is no active constraints on these variables. First, we saw that the necessary conditions for a minimum are, while sufficient conditions for a local minimum are given by. Thus, the only difference between these two set of conditions is, for a local minimum, the second derivative of the index function must be a positive definite. Now let us extend this problem by assuming that we have equality constraints on some of the decision variables. And we need to drive necessary conditions for having a stationary point. Note that we are interested first at driving conditions for determining stationary points. And then we will find how to specify these points as minimum. First things first, let me introduce the main problem now. We have m decision variables u1 through um, that we want to minimize an index of performance capital L function. Note that our new index of performance capital L is now a function of our decision variables u, as well as new variables called the state variables x1 through xn. Thus, we have n plus m variables to deal with. The n state parameters are subjected to some constraints f1 through fn as shown. As we did with problem in part 1, let us stick all these variables and functions in vector format. So, we have the vector u for our decision variables u1 through um. And we have the vector x for state variables x1 through xm. And finally, the vector f which combines the constraints on the state variables. Based on these vectors, we now can reformulate our original problem as: find the decision vector u, that minimizes a scalar performance function L capital of vectors x and u. The state vector x is subjected to set of constraints f, that could be written as f of x and u equal to 0. This is a set of n equations. For the given parameter optimization problem, the choice of which parameters to be the decision parameters is not unique. However, this choice must be done such that the decision variables um should determine the state variables xn through the given constraint functions. If both functions L and Fn are linear in the parameter variables u and x, then, in general, a minimum does not exist. Therefore, inequality constraints in such cases are essential to make the problem meaningful. Problems with linear index of performance function, along with linear inequalities, are called linear programming problems. Now, let us assume that we have some nonlinearities in the function capital L or the constraint functions fn, or both. These nonlinearities, of course, don't ensure that a minimum exists. As stated previously, a stationary point is found when the first derivative of the index function is equal to 0, for some du, but now, we hold df equal to 0 as well. To accomplish this, we simply adjoin the constraint function vector f to the index function capital L through a set of constant and undetermined multipliers lambda 1 through lambda n, as shown by the following relation. More comprehensively, let us define the vector lambda, as shown. Then, we can write the following vectoroform of this function as. So, we have the function h of x u and lambda, which simply equals to the summation of the index function L, with the constraint function f that is pre-multiplied by the constant and unknown vector lambda. In order to find the stationary point for this case, we can differentiate the function capital H as shown, in which we have delta h for delta x, and delta h for delta u, as shown. As we have driven all the necessary derivatives, we can now apply our desires, in order to solve for the stationary point when having equality constraints. First, we are interested in how the function capital H, or more precisely, capital L, changes as the decision vector u changes, regardless of how the state vector x changes. Thus, we can equalize delta h for delta x to 0. This gives a way to determine the vector lambda, as shown. Therefore, we can eliminate delta h for delta x in the function of capital H. Now let us introduce another required point for our central problem. Suppose we have found some initial values for decision vector u, such that the constraint f of x and u is satisfied. At this point, and from the equation of the capital H, we can have L equal to H. This will give the following relation, as well. Now, in our definition of the stationary point, we have said that dl is equal to 0 for some du. Thus, from the final relation of dl or dh, the only way to have dl equal to 0, is when delta h for delta u is 0. Based on that, we can also eliminate delta h for delta u in the relation dl. Please don't forget that delta h for delta u is the gradient of the original index function capital L, with respect to the decision variable u, while holding the constraint function f of x u equal to 0. To sum up what we have driven so far, in determining a stationary point for an optimization problems with equality constraints, we need to solve for the parameters um and xn, from the following equations. The constraint functions, the derivatives of the function h with respect to the state variable vector xn, as well as, to the decision vector Remember that, the h function is given as the summation of the index function L, and the constraint functions f, which is pre-multiplied by the multiplier lambda. Please, notice the followings. First, the vector lambda is a constant, unknown vector that needs to be computed in the process of solving for the optimal point. And second, through this set of equations, we totally have to solve for two n plus m equations, which represent the involved parameters xn, fn, and um. Now, let me introduce an example to illustrate what we have covered so far. In this example, we want to compute a scalar parameter u, that gives a stationary point for the given function L. The computed value of u is subjected to the shown constraint f of x and u. The state variable x is also a scalar, whereas a, b, m, and c are some constants. As illustrated by the figure, the function L is an ellipse with increasing size, whereas the function f is a fixed straight line. It is obvious that the minimum value of L satisfying the given constraint f is obtained when the ellipse is just tangent to the straight line given by the constraint. However, analytically, we can compute such point by, first, constructing the h function as, which, in terms of the given functions, is having the following form. Now we can use the driven necessary conditions for a stationary point, where we have the three conditions given as. Applying these conditions with the given functions by the example, we could have the following set of equations, where we have three unknowns, x, u, and lambda. Solving these equations, result in the following solution. Utilizing the values of x and u, the minimum value of the index function is as shown. Notice that, in this example, the relations given by the index function, as well as the constraint function, are quite simple, and the solving for the stationary point was straightforward. For complicated relations, however, numerical methods must be employed to determine the values of the decision variable u, which optimizes the given index of performance. In the upcoming video, I will cover the driving of sufficient conditions for a local minimum, when equal constraints are active. Thanks, again for watching the video. See you in a new video, hopefully.